Chapter 17, Analysis of Factor-Level Means. The Introduction. In Chapter 16, we discussed the F-test for determining whether or not the factor-level means μi differ. This is a preliminary test to establish whether detailed analysis of the factor-level means is warranted. When this test leads to the conclusion that the factor-level means μi are equal and ANOVA model is appropriate, no relation between the factor and the response variable is present, and usually, no further analysis of factor means is therefore indicated. On the other hand, where the F-test leads to the conclusion that the factor-level means μi differ, a relation between the factor and the response variable is present. In this latter case, a thorough analysis of the nature of the factor-level means is usually undertaken. This is done in two principal ways. First, the analysis of the factor-level means of interest using estimation techniques, and second, the statistical test concerning the factor-level means of interest. Often, the analysis of factor-level means combines the two approaches. For instance, a two-sided confidence interval may be constructed initially for an effect of interest. A test concerning this effect is then carried out either by determining whether or not the confidence interval contains the hypothesized value or by constructing the appropriate test statistic. When many related comparisons are to be made, testing often precedes estimation. This occurs, for instance, when each factor-level effect is compared with every other one, and the number of factor-level levels is not small. Here, statistical tests are often performed first to determine the active or statistically significant set of comparisons. Estimation techniques are then used to construct confidence intervals for the active comparisons. Special simultaneous estimation and testing procedures called multiple comparison procedures are required when a series of interval estimates or tests are performed. These multiple comparison procedures preserve the overall confidence coefficient 1 minus alpha, or the overall significance level alpha, for the family of inferences. Throughout this chapter, we continue to assume the usual single-factor ANOVA model. The cell means version of this model was given as y sub iij equals μi plus error ij, where μi are parameters and error ij are independent normal with mean 0 and variance sigma squared. The plots of estimated factor-level means. Before undertaking formal analysis of the nature of the factor-level effects, it is usually helpful to examine these factor effects informally from a plot of the estimated factor-level means y sub I dot bar. We shall take up three types of plots. First, a line plot, then a bar graph, and then a main effects plot. All three plots are appropriate whether the sample sizes ni are equal or not. A line plot of the estimated factor-level means simply shows the positions of the yi dot on a line scale. It is a very simple but effective device for indicating when one or several factor-level means may deserve substantially from the others. If we look at this figure, presented a line plot of the estimated factor-level means yi bar for the Kental Food Company example. It is clear that design 4 led by far the highest mean sales in the study, and that package designs 1 and 2 led to the smallest mean sales, which did not differ from each other. The purpose of the formal inference procedures to be taken up shortly is to determine whether the pattern noted here reflects underlying differences in the factor-level means μi, or is simply the result of random variation. Now the bar graph and the main effects plot. Bar graphs and main effects plots are frequently used to display the estimated factor-level means in 2 dimensions. Both can be used to compare the magnitudes of different factor-level means. In a bar graph, vertical bars are used to display the estimated factor-level means. In a main effects plot, a scatter plot of the estimated factor-level means is provided, and the plot symbols are connected by straight lines to visibly highlight potential trends in the cell means. Note that these trend lines are not particularly meaningful for quantitative factors. For this reason, main effects plots are most appropriate for quantitative factors. In some packages, the main effects plot also displays the overall mean using a horizontal line, permitting the visual comparisons of factor-level means with the overall mean. A, we could see as a bar graph, and B is a main effects plot. Estimation and testing of factor-level means. Inferences for factor-level means are generally concerned with one or more of the following. First, a single factor-level mean μi. Second, a difference between two factor-level means. Third, a contrast among factor-level means. And lastly, a linear combination of factor-level means. So the inferences for single factor-level means. The estimation. An unbiased point estimator of the factor-level mean μi is given by μi hat equals yi bar. This estimator has mean and variance. The mean is mu I and the variance is sigma squared over ni. The latter result follows because 16.43 indicates that yi bar equals mu I plus error I bar dot. The sum of a constant plus a mean of ni independent error ij error terms, each of which has a variance of sigma squared. Further, yi bar dot is normally distributed because the error terms error ij are independent normal random variables. The estimated variance of yi bar dot is denoted by s squared and is obtained as usual by replacing sigma squared by the unbiased point estimator MSE. So it becomes MSE over Ni. The estimated standard deviation S of yi bar dot is the positive square root of 17.4. It can be shown that yi bar dot minus mu I over S of yi bar dot is distributed as T for n sub T minus R for the ANOVA model, where the degrees of freedom are those associated with MSE. The result follows from the definition of T, since yi bar is normally distributed and MSE over sigma squared is distributed independently of yi bar dot as chi squared of nt minus r over nt minus r, according to the following theorem. For ANOVA model, SSE over sigma squared is distributed as chi squared with nt minus r degrees of freedom and is independent of yi bar dot through yr dot bar. It follows directly from 17.5 that the 1 minus alpha confidence limits for yi are yi bar plus or minus t of 1 minus alpha over 2 and nt minus r times s of yi bar dot. The testing. The confidence interval based on the limits can be used to attest a hypothesis of the form H naught being yi equals c and the alternative hypothesis of mu y not equaling c, where c is an appropriate constant. We conclude the null hypothesis at level of significance alpha when c is contained in the confidence interval, and we conclude the alternative hypothesis when the confidence interval does not contain c. Equivalently, we can compute that the test statistic is T star equals yi bar dot minus c over s of y bar I dot. The test statistic T star follows a T distribution with nt minus r degrees of freedom when the null hypothesis is true. Consequently, we conclude the null hypothesis whenever the absolute value of T star is less than or equal to T of 1 minus alpha half nt minus r degrees of freedom. Otherwise, we conclude the alternative hypothesis. The inferences for difference between two factor level means. The estimation. Frequently, two treatments or factor levels are to be compared by estimating the difference d between the two factor level means, say mu I and mu I apostrophe. So d equals mu I minus mu I apostrophe. Such a difference between two factor level means is called a pairwise comparison. A point estimator of d is denoted by d hat, which is equal to yi bar dot minus yt yi apostrophe bar. This point estimator is unbiased, so the mean is mu I minus mu I apostrophe. Since they are independent, the variance of d hat follows the sigma squared of yi bar dot plus the sigma squared of yi apostrophe bar, which is equal to the sigma squared of 1 plus n over I plus 1 over n I apostrophe. The estimated variance of d hat is MSE of the same value. Finally, d hat is normally distributed because d hat is a linear combination of independent normal variables. It follows from these characteristics that theorem 17.6 and the definition of t is the d hat minus d over the s of d hat is distributed as t of nt minus r for ANOVA model, 17.1. Hence, the 1 minus alpha confidence limits for d are d hat plus or minus t of 1 minus alpha half nt minus r s of d hat. The testing. There is often interest in testing whether two factorable means are the same. The alternatives here are of the form, the null hypothesis is mu I equals mu I apostrophe, and the alternative hypothesis is that they are not equal. The alternatives can be stated equivalently as the follows. The null hypothesis is mu I minus mu I apostrophe equals 0, and the alternative hypothesis is that they are not equal to 0. We conclude that the null hypothesis is reached at the alpha level of significance if 0 is contained within the confidence limits. Otherwise, the conclusion is that the alternative hypothesis is reached. An equivalent procedure is based on the test statistic, where the t star equals the d hat over the s of d hat. The conclusion is that the null hypothesis is reached if the absolute value of t hat, a t star, is less than or equal to t of 1 minus alpha half with nt minus r degrees of freedom. Otherwise, the alternative hypothesis is concluded. The inferences for contrast of factor level means. A contrast is a comparison involving two or more factor level means and includes the previous case of a pairwise difference between two factor level means in 17.10. A contrast will be denoted by L and is defined as a linear combination of the factor level means mu I where the coefficients ci sum to 0. So we have L equals the summation of I equals 1 to R of ci mu I, where the summation of I equals 1 to R of ci equals 0. The estimation is an unbiased estimator of a contrast L, which is L hat equals the summation of I equals 1 to R of ci yi bar dot. Since the yi bar dot are independent, the variance of L hat is sigma squared of summation I equals 1 to R of ci squared over ni. An unbiased estimator of this variance is MSE of the summation of I equals 1 to R of the same value. L hat is normally distributed because it is a linear combination of independent normal random variables. It can be shown by the theorem 17.6, the characteristic of L hat just mentioned, and the definition of T that L hat minus L over S of L hat is distributed as T and T minus R for ANOVA model 17.1. Consequently, the 1 minus alpha confidence limits for L are L hat being plus or minus T of 1 minus alpha hat alpha squared half with nt minus r degrees of freedom times s of L hat. Testing. The confidence interval based on the limits is 17.24. Can be used to test a hypothesis to the form where the null hypothesis is L equals 0 and the alternative hypothesis is L does not equal 0. The null hypothesis is concluded at the alpha level of significance if 0 is contained in the interval. Otherwise, the alternative hypothesis is concluded. An equivalent procedure is based on the test statistic, where T star equals L hat over S over L hat. If the absolute value of T star is less than or equal to T of 1 minus alpha over 2 with nt minus r degrees of freedom, the null hypothesis is concluded. Otherwise, the alternative hypothesis is concluded. The inferences for linear combinations of factor level means. Occasionally, we are interested in a linear combination of factor level means that is not a contrast. We define a linear combination of the factor level means mu I as L equals the summation of I equals 1 to R of ci mu I, with no restrictions on the coefficient ci. Confidence limits and test statistics for a linear combination L are obtained in exactly the same way as for those for contrast by means of 17.24 and 26 respectively. The point estimator 0.20 and estimated variance of 22 are still applicable when the summation of ci does not equal 0. The single degrees of freedom tests. The alternatives for tests concerning a factor level mean in 17.8, a difference between two factor level means in 17.17a, and a contrast of factor level means in 17.25 are all special cases of a test concerning a linear combination of factor level means, where the null hypothesis is the summation of ci mu I equaling c, and the alternative hypothesis is the summation of ci mu I not equaling c, where the ci and c are appropriate constants. The test statistics 17.9, 17.18, and 17.26 can each be converted to an equivalent F-star test statistic by means of the relation in 8.50a, where F-star is equal to the T-star being squared. The test statistic F-star follows that F is 1 nt minus r distribution when the null hypothesis holds. Note that the numerator degrees of freedom are always 1. Hence, these tests are often referred to as single degree of freedom tests. The T-star version of the test statistic is more versatile because it can be used for one-sided tests, while the F-star version cannot. Lastly, the need for simultaneous inference procedures. The procedures for estimating and testing factor level means discussed up to this point have two important limitations. First is the confidence coefficient 1 minus alpha for the estimation procedures described is a statement confidence coefficient and applies only to a particular estimate, not to a series of estimates. Similarly, the specified type 1 error rate, alpha, applies only to a particular test and not to a series of tests. Secondly, the confidence coefficient 1 minus alpha and the specified significance level alpha are appropriate only if the estimate or test was not suggested by the data. The first limitation is familiar from regression analysis. It is particularly serious for analysis of variance models because frequently many different comparisons are of interest here, and one needs to piece the different findings together. The same concern for assurance of correct conclusions exists when the inferences involve tests. An analysis of factor means by testing procedures usually involves several single degree of freedom tests to answer related questions. The second limitation of the procedures for estimating or testing factor level means discussed so far, namely, that the estimate or test must not be suggested by the data, is an important one in exploratory investigations where many new questions are often suggested once the data are being analyzed. The process of studying effects suggested by the data is sometimes called data snooping.